Hello everybody, and welcome to the beginning of section 2.4. We are looking at page 60 in the workbook, and in this section we're going to be talking about invertibility and isomorphisms. I think the best way to illustrate these concepts is just to dive in with kind of a preliminary example here. So let's look at example 1 together. So let v equal r2 and let w equal p1 of r. They ask us kind of a deliberately vague question here. Are the vector spaces v and w different? Okay, well, if we take that question very literally, the answer is obviously no. These two vector spaces are not the same. R2 is a set of ordered pairs, and P1 of R is a set of polynomials. Okay, but what we're going to discover in this example is that even though the vector spaces are different, there's some similarities, there's some parallels going on. Okay, so for example, let's do an ordinary addition calculation in R2. Okay, so we could take kind of two generic looking ordered pairs, maybe A, B, and C, D, add those together, and we would get A plus C and B plus D. Okay, there's a typical calculation in the vector space V. What's interesting is that there's a corresponding calculation in the vector space W. Okay, so the ordered pair AB, we can think of that as kind of corresponding to the polynomial A plus BX. Okay, and similarly, CD is corresponding to C plus DX, and we could do the addition of those two polynomials in W and get A plus C plus B plus dx, and then there's kind of a natural correspondence between the ordered pair A plus C, B plus D, and the polynomial below it. Okay, so down here on this line, we've got a typical calculation in W. Okay, and we can notice kind of a parallel with scalar multiplication as well. Okay, if we take a scalar C and multiply it by the ordered pair AB, okay, we're just going to get CA and CB. There's kind of a typical multiplication calculation in the vector space V. And there's a corresponding calculation in W for that as well, where we take C times the polynomial, A plus BX, do the multiplication, and we get CA plus CBX. Okay, in W. Okay, and there's a natural correspondence between the ordered pair and the polynomial again. Okay, so what we're noticing here is that even though these vector spaces are different, they have different objects, there's a definite analogy between them. So let's say it this way. Okay, an observation that we can make here is that V and W seem analogous as vector spaces. Okay, to make that a little bit more specific, what we mean, this correspondence that we're talking about between the spaces can be illustrated by a function, t that goes from V to W, defined by t of the ordered pair A and B equals the polynomial A plus BX. That's exactly the correspondence that we noticed looking back at our work up here. Okay, the ordered pair AB, we kind of made the decision or made the observation that it's kind of analogous to the polynomial A plus BX. And this function that we just defined, t, that goes from V to W, has a number of interesting properties. Okay, it's linear. We could check that. It's one-to-one and onto. And because it's both one-to-one and onto, it's also invertible. Okay, and this type of a function is going to play a very big role in this section that we're studying. In the next video, we'll kind of formalize this into a couple of definitions.